Today, in Shanghai, the Tsungdao Lee Institute is kicking off a summer school on particle physics, the final act of a week-long symposium commemorating the 70th anniversary of one of the most shocking discoveries in the history of science, the violation of parity in weak interactions. And in a lecture hall at the University of Hamburg, Nobel laureate Reinhard Genzel is addressing an audience on the mysteries of the cosmos. But there is another anniversary today, one that is perhaps less celebrated but no less profound. On this day, 99 years ago in 1927, a baby boy was born in New York City to a Jewish family of Polish descent. His name was Martin Lewis Perl, and he would grow up to discover a particle that should not have existed, a particle so heavy and so fleeting that it rewrote our understanding of the very architecture of matter. He discovered the tau lepton, the heaviest member of the family of particles that includes the electron, the particle that lights up your screen and powers your thoughts. The story of the tau is a story of persistence, of trusting the data even when it makes no sense, and of the beautiful, relentless logic of the Standard Model. It is also a story that connects directly to the man whose name is on this channel, Richard Feynman, because the tau lepton is a monument to the power of quantum field theory, the very framework that Feynman helped to build. To understand the significance of Martin Perl's discovery, you have to first understand the world of particle physics in the decades before he came along. In the early 1930s, physicists knew of only two fundamental particles that carried electric charge: the electron and the proton. The neutron had just been discovered, and the positron, the antimatter counterpart of the electron, was confirmed in 1932. It was a tidy, almost minimalist picture. But then came the 1930s and the discovery of a new particle in cosmic rays. It had the same charge as the electron, the same spin, the same fundamental properties, but it was about 200 times more massive. It was a heavier version of the electron, and it was completely unexpected. Physicists called it the muon, and they were deeply puzzled. As the physicist Isidore Isaac Rabi famously quipped when he heard the news, "Who ordered that?" The muon seemed superfluous, an unnecessary complication. Why would nature need a heavier copy of the electron? It didn't seem to serve any obvious purpose. It was a mystery, and it remained a mystery for decades. Then, in the 1950s and 1960s, as particle accelerators grew more powerful and the zoo of discovered particles expanded into a bewildering menagerie, physicists began to discern a pattern. It turned out that the electron and the muon were not isolated oddities. They were members of a family, a group of particles called leptons, from the Greek word for small or fine, and each charged lepton had a corresponding neutrino, an almost massless neutral partner. The electron had the electron neutrino. The muon had the muon neutrino. It was a neat two-generation structure, but it begged the question, was that the end of the story? Or were there more generations, more families waiting to be discovered? Martin Perl entered this field in the 1960s after a circuitous path that took him from a childhood in the gritty streets of Brooklyn to a degree in chemical engineering, and then, finally, to a PhD in physics under the legendary E.Y. Rabi at Columbia University. He worked at the University of Michigan before moving to the Stanford Linear Accelerator Center, SLAC, in 1963. SLAC was a new facility, housing the longest linear accelerator in the world, a 2-mile-long machine that could accelerate electrons and positrons to nearly the speed of light. Pearl was part of a group that was designing a detector for a new collider, a machine that would smash electrons and positrons head-on. The detector was called the SLAC Lawrence Berkeley Lab Magnetic Detector, later known as the Mark I. It was a massive, complex apparatus, a cylindrical behemoth of magnets and wire chambers and calorimeters designed to capture the debris of these high-energy collisions. And Pearl had a hunch. He believed that if there was a third generation of leptons, a heavier cousin of the electron and the muon, it would be produced in these collisions. And he believed that he could find it. The problem was that the signal for a new heavy lepton would be incredibly subtle. When an electron and a positron annihilate, they can produce a pair of heavy leptons. These leptons would be unstable. They would decay almost instantly into lighter particles, typically into a muon or an electron, plus some neutrinos. The signature would be an event where you saw an electron and a muon coming out of the collision, but with missing energy and momentum that could only be explained by the undetected neutrinos. It would look like a background event, a random coincidence. But Pearl and his team, including a brilliant young physicist named Gary Feldman, realized that if they looked carefully at the data, they could distinguish these events from the background. They would see an electron and a muon appearing back to back with no other particles and with a specific amount of missing energy. This was the signature of a heavy lepton decay. It was a needle in a haystack. And for years, they found nothing. They sifted through tens of thousands of collisions. They refined their analysis. They improved their detector. And finally, in 1974, they started to see a few events that matched the signature. They were tentative, uncertain. They needed more data. They ran the collider for months, accumulating more and more collisions. And the events kept appearing. They were real. In 1975, Perl and his collaborators published a paper announcing the discovery of a new particle. They called it the heavy lepton, and they designated it with the symbol U for unknown. They were cautious, almost painfully so. They emphasized that they could not definitively rule out alternative explanations. They invited other physicists to scrutinize their results, to check their calculations, to look for flaws. It was a masterpiece of scientific humility. And the physics community did scrutinize it. They debated it. They argued about it. Some were skeptical, convinced that the events were just a cleverly disguised background. Others were intrigued. And then, over the next few years, other experiments at SLAC and elsewhere confirmed the discovery. The particle was real. It was a new lepton, a third generation. It was eventually named the tau from the Greek letter tau, and it was a bombshell. The tau lepton was about 3,500 times more massive than the electron. It had a lifetime of only about 10 to the minus 13 seconds, vanishingly short, and it decayed through the weak interaction, the same force that governs radioactive decay. Its discovery confirmed that the electron and the muon were not the whole story. There was a third family. And if there were three families of charged leptons, there must be three families of quarks as well. And indeed, the tau was soon followed by the discovery of the bottom quark and the top quark, completing the three-generation structure of the Standard Model. Now, let me connect this to Feynman. Feynman was not directly involved in the discovery of the tau. He was, by then, focused on other problems, including his work on the theory of quantum chromodynamics and his investigations into the nature of the weak interaction. But the tau lepton was, in a very real sense, a prediction of the theoretical framework that Feynman helped to create. That framework is quantum field theory, and its most successful incarnation is the Standard Model. Feynman's path integral formulation and his Feynman diagrams provided the mathematical language that physicists use to calculate the properties of particles and their interactions. The discovery of the tau was not just an experimental triumph, it was a confirmation of the deep structure of the theory. The theory predicted that there could be multiple generations of leptons, even though it didn't specify how many. The fact that a third generation existed was a validation of the entire enterprise. It was a sign that the physicists were on the right track, that their mathematical descriptions of the subatomic world were not just elegant abstractions, but accurate reflections of reality. But the tau lepton also presented a profound mystery, a mystery that remains unsolved to this day. Why are there three generations? Why not one? Why not four? The Standard Model has no answer. It simply accepts the three generations as a fact of nature, an input parameter that must be measured, not explained. This is deeply unsatisfying to physicists. It is the kind of question that Feynman loved to ask. He would have been troubled by the apparent arbitrariness of it all. He would have wanted to know why. And that is the beauty of the tau. It is not just a particle. It is a question mark. It is a pointer to a deeper theory, a theory that will one day explain the pattern of generations, the masses of the particles, the fundamental constants of nature. We are not there yet, but the tau is a signpost, a guidepost, a reminder that the universe is still holding out on us. It has secrets it has not yet revealed. Consider the mass of the tau. It is 3,500 times the mass of the electron. Why? Why is it so heavy? Where does that mass come from? In the Standard Model, the mass of a particle comes from its interaction with the Higgs field. The more a particle interacts with the Higgs field, the heavier it is. But why does the tau interact so strongly with the Higgs field while the electron interacts so weakly? The answer is not known. It is related to the Yukawa couplings, a set of arbitrary parameters that physicists have to put into the theory by hand. They are not predicted. They are measured. And the fact that they span such a huge range from the electron to the top quark is one of the great puzzles of particle physics. It is a problem that Feynman would have recognized as a challenge to the very idea of a fundamental theory. A truly fundamental theory should not have arbitrary parameters. It should explain everything from first principles. The fact that the Standard Model has so many free parameters is a sign that it is not the final word. It is an effective theory, a low-energy approximation to a deeper reality. And the tau lepton, with its stubborn, unexplained mass, is a constant reminder of that deeper reality. Let me take you inside the detector, inside the Mark I, to feel the thrill of discovery. Imagine you are sitting at a control console surrounded by blinking lights and humming electronics. You are looking at a computer screen that shows the tracks of particles emerging from a collision. Most of the events are boring. They are the same old things, the same familiar patterns, the same known particles. But then every once in a while, you see something strange. You see an electron and a muon emerging from the collision point back to back with no other tracks. It is a clean event, a beautiful event. And you know instantly that this is not background. This is something new. This is the signature of a heavy lepton, a particle that has never been seen before. You feel a jolt of adrenaline. You feel the hairs on the back of your neck stand up. You know that you are witnessing something that no human has ever seen. That is the moment of discovery. That is the moment that Perl and his team experienced again and again as they accumulated the data that would change physics forever. Perl was not a flamboyant man. He was quiet, methodical, persistent. He was the opposite of the popular image of a brilliant, eccentric physicist. He was a plodder, a meticulous craftsman who built his detector piece by piece and analyzed his data line by line. He was not a theorist. He was an experimentalist, and he trusted his instruments. He was also deeply skeptical of his own results. He knew that the history of physics was littered with false discoveries, with particles that turned out to be statistical flukes or instrumental artifacts. He was determined that his discovery would not be one of them. That is why he published his results with such caution. That is why he invited scrutiny. That is why he spent years refining his analysis before he was finally convinced that the tau was real. And when the Nobel Prize came in 1995, shared with Frederick Reines for the discovery of the neutrino, Perl accepted it with characteristic grace. He had earned it, not through a flash of brilliance, but through decades of hard work. His story is a testament to the fact that science is not just about genius, it is about persistence. It is about showing up every day and doing the work, even when the work is tedious, even when the results are negative, even when everyone else has given up. Now let me bring this back to the present. June 24th, 2026. The tau lepton is now a familiar part of the particle physics landscape. It is produced routinely at the Large Hadron Collider at CERN, and it is studied in exquisite detail. Physicists have measured its properties with extraordinary precision. They know its mass to better than 1 part in a million. They know its lifetime to a fraction of a percent. They have measured its decay modes, its spin, its magnetic moment, and everything they have found is consistent with the Standard Model. The tau is a well-behaved, predictable particle, but it is also, in a sense, a disappointment because it has not revealed any new physics. It has not pointed the way to a deeper theory. It has not explained the mystery of its own existence. It has simply confirmed what we already know. And that is a problem because the Standard Model, for all its successes, is incomplete. It does not explain dark matter. It does not explain dark energy. It does not explain why the universe is made of matter and not antimatter. It does not explain gravity. It does not explain the pattern of particle masses. And the tau, for all its heavy mass, has not helped us answer any of these questions. It is a beautiful, elegant, and profoundly frustrating particle. But that frustration is exactly what drives physics forward. The fact that the tau has not revealed new physics is not a failure. It is a constraint. It tells us that whatever new physics exists, it must be very well hidden. It must be at higher energies or in more subtle interactions than we have yet probed. It tells us that we need bigger accelerators, more sensitive detectors, more clever experiments. It tells us that the next great discovery will not be easy. It will require the same kind of persistence, the same kind of meticulous craftsmanship, the same kind of trust in the data that Martin Perl embodied. And when that discovery comes, it will be built on the foundation that Perl helped to lay. It will be a testament to the power of the scientific method, the method that Feynman championed, the method that says, look at the data, trust the data, let the data guide you, even when it leads you to places you never expected. So on this day, June 24th, 2026, as physicists in Shanghai gather to discuss the future of their field, and as they reflect on the legacy of parity violation, let us also remember Martin Perl, the quiet man from Brooklyn who discovered a particle that should not have existed. Let us remember the tau lepton, the heavy, fleeting ghost that rewrote our understanding of the universe. And let us remember that the universe is still full of mysteries, still full of particles waiting to be discovered, still full of questions waiting to be answered. The tau was a door. It opened onto a new landscape, a new generation of particles, but that landscape is still largely unexplored. There are still doors to be opened, still secrets to be revealed, and the next door might be opened by a young physicist sitting in a lecture hall in Shanghai or Hamburg right now, listening to talks about parity and neutrinos and the origins of the cosmos. That young physicist might be the next Martin Perl. That young physicist might discover the particle that finally explains why there are three generations, why the tau is so heavy, why the universe is the way it is. And that is the excitement of physics. That is the joy of discovery. That is why we are here. Stay curious.